All right, so I'm going to work through a couple of Chapter 9 questions here from your Chapter 9 homework. Specifically, what I'm going to do is I'm going to jump on with question number 1 from Chapter 9. And what this is all about is valence electrons. Now, anytime you look at a particular element or particular atom on the periodic table, you'll be able to see approximately the number of protons, or well, the number of protons based on the atomic number. You'll be able to determine the atomic mass of that individual atom. And then you'll also be able to deduce, based on the number of protons, the number of electrons an atom has. However, what you kind of need to worry about and need to be more concerned and curious about is the number of valence electrons. V-A-L-E-N-C-E electrons. So our number of valence electrons is basically the number of electrons that are going to be involved in pairing. So those are your outermost electrons. So outermost E. Now, this particular question, number 1, has a total of 4 different elements that are involved. And you're asked about Be, beryllium, P, phosphorus, F, fluorine, and Kr, krypton. Okay. Now I think this is good because it gives us a good range. So the first element, and I'd like you to be able to reference your periodic table, which I'm going to toggle back and forth between my periodic table and my whiteboard here. But if you look at this, what we've got is Be, our first element, beryllium, is right here. Okay. Now beryllium in group 2, well, beryllium, one of the things that you need to know about it is it's generally going to form a +2 ion, but that's also a good way to determine the number of valence electrons. So Be has a total of 2 valence electrons. Okay, the same is also going to be true for magnesium, calcium, strontium, barium, radium. So group 2, 2 valence electrons. Okay, now the next question was all about phosphorus. Okay, phosphorus, how many valence electrons does that have? Well, actually, let me go ahead and jump back to my whiteboard here. Be is going to have 2 valence electrons. Then next is going to be phosphorus. So I'll jump back to my periodic table. Phosphorus is right, oh, not in annotate mode. Phosphorus is right here. Lo and behold, we'll scribble at the 1 and there's our answer, 5 valence electrons. After that is fluorine. Scribble at the 1, 7 valence electrons. And the final one is Kr, krypton. So simply identifying the number of valence electrons is going to be very productive whenever you're trying to, well, think about bonding. Now, with that said, we've talked about an octet rule. So each element wants to have a total of 8, or each atom wants to have a total of 8 electrons surrounding it. So if you look at something like krypton with 8 electrons around it, well, if krypton's going to be involved in any sort of compound formation, well, it's going to exceed the octet rule. It also should tell you that krypton, Kr, with a total of 8 electrons around it, it's pretty much happy. It's pretty content where it is. So it generally doesn't really need to change, or it doesn't need to be involved in bonding, and generally isn't involved in bonding. Okay, so let me go ahead and fill these answers in from what we got. 5, 7, and 8. Okay, so the next question is, well, question number 2. And I'm just going to go straight on to that. Question number 2 says, identify the core and valence electrons for each atom. Okay, for this, we're given 3 different atoms, 3 different elements. We're given Xe for xenon. We are given Ca for calcium. And finally, we are given Br for bromine. Okay, so what we're asking about is core electrons versus the valence electrons. So what I want you to think about with that is, what's the total number of electrons? Okay, so first and foremost, I'm going to write xenon has a total of 54 top electrons. Okay, now this is going to be core plus valence. So This number right here, 54, can come from the periodic table. And I'm going to go ahead and fill in the rest from the periodic table. Calcium is 20. Bromine is 35. Okay, so if my total number of valence electrons is equal, or sorry, my total number of electrons is equal to my atomic number, because I'm talking about a neutral atom here, well then, and my valence electrons are basically equal to the row in which that element is found on the periodic table, then we're looking at, well, xenon has 54 total electrons, 8 valence electrons, therefore it has 46 core electrons. Okay, now calcium has 2 valence electrons, and therefore it has 18 core electrons, because 18 plus 2 equals 20. Bromine has a total of 35 electrons, and bromine also has 7 valence electrons because it's in group 7 of the periodic table. And then finally, bromine, well, it's going to have 28 core electrons. All right, so that's really what we're talking about, core versus valence electrons. Valence are going to be involved in bonding. Core electrons are not going to be involved in bonding. Okay, so my next question is going to be question number 3. Now, question 3 reads, classify each statement about effective nuclear charge as true or false. So effective nuclear charge is identified as ZEFF. Okay, so what that basically rounds up to is it's almost like saying, when you take into consideration all of the other electrons that a electron senses, or do all electrons sense the same pull from the nucleus? Now, I'd like to go ahead and kind of visualize or draw this concept, or draw this idea. Okay, so at our center here, we've got our nucleus, and that's where our protons are. Now, let's say that there are 10 protons there. Then we've got these 2 electrons that are in my 1s orbital. Do you think, based on this representation, with only 2 electrons drawn, those 2 electrons are going to feel the pull of, well, 10 protons? And they're going to feel it pretty evenly. But then we expand outward. Boom, boom. Okay, so I'm going to label my electrons 1 and 1, 2 and 2. Are the electrons that are labeled 2 going to sense the same pull from our protons as those electrons that are labeled 1? No, they're not. And so that's why we have this effective nuclear charge. Are they going to feel the pull of that that nucleus equally? No, they're not, because what we're going to have is this, what's known as a shielding effect. So these electrons that I'm circling right now, they're basically going to kind of, it's almost like they're boxing out, to use a basketball analogy. They see the rim and they're going to back up so that they can prevent anyone else from getting the ball. And the ball in this metaphor would be the positive charge of the nucleus. Okay, so a couple of statements. The first statement, effective nuclear charge does not depend on the number of electrons present in an atom. Effective nuclear charge does not depend on the number of electrons. It absolutely does, because those electrons are going to be placed in different areas. So the more electrons, the higher number of electrons, or the farther that those electrons are distributed. So that would be a false statement. Okay, now across a period. So a period is different from a group. Groups go up and down. Groups are our columns, and periods are our left to right rows. So across a period, effective nuclear charge increases and atomic size increases. Well, let's see. Atomic size trend. Well, if we looked at our atomic size trend, it's going to be down and to the left. So across, it kind of puts a little bit of confusing language in there. This is, so if you're reading left to right, or if you're reading right to left, well, our atomic size is going to increase basically across a period and across a group. So that part of it's true. But our effective nuclear charge is not going to increase. So that would be a false statement. Okay, so we've got two falses. And our third statement here, in a N atom, a 1s electron has a greater effective nuclear charge, or greater ZEFF, than a 2s electron does. And that would be a true statement, because those first two electrons in the 1s orbital, they're going to feel the pull of that nucleus more so than the 2s electrons. Because remember, the 1s electrons, they're kind of boxing out. They're putting everything behind them. Okay, so that would be a true statement. Effective nuclear charge increases from left to right across the period on the periodic table. Okay, left to right. That would be a true statement. From left to right on the periodic table, the effective nuclear charge is going to increase. Okay. A 1s electron is, or 1s electron in a beryllium atom has a smaller ZEFF, or Z effective nuclear charge, than a 1s electron in a lithium atom. Okay, so what's our difference between those? So the difference between them is that our beryllium atom, well, beryllium's going to have a couple more protons than a lithium atom is, and so it's going to have a greater charge. So that would be a false statement. Now, electrons in an s orbital are more effective than those in other orbitals at shielding other electrons from the effective nuclear charge. Well, let's think about this. Those s orbitals, those are the ones that are as close as possible, whether it's the 1s, 2s, 3s, or 4s. Those electrons are as close to the nucleus as possible at that kind of energy level. So they're basically forming a sphere and pushing everything else behind them. So that would be a true statement. Okay, so I think that one of the things that's a little bit awkward and confusing about this is that across a period, a ZEFF increases, atomic size increases. That language, I don't particularly like it because it doesn't give a reference point of left to right or right to left. And so that's not the type of question, or that's not the type of wording that you would expect, or you should expect from a question like this on the exam from me. All right, well, this is the first 3 questions for your chapter number 9 homework. I hope this was helpful, and have a good one.